Okay, in this video we are going to have a look at a couple of accelerometers and some programming techniques. Now the first accelerometer is the LIS3DH, which you can see on this module. It's a 3-axis accelerometer and it's made by ST Microelectronics, the same company who made this ARM microcontroller, which is the STM32F411, which is a Cortex M4 ARM microcontroller. Now the microcontroller is connected up to the LIS3DH by the SPI bus. And I originally made this circuit for somebody who needed a parachute deployment system for a model rocket. So when the model rocket is under power, engine is creating thrust, we're going to have some G values on the X and Y and Z axis. Now when we go into a free fall, when the engine quits, this LED will come on, which will deploy the parachute. So as we're flying, you can see the LED is not coming on, but as soon as I go into a free fall, so I'll drop it, LED comes on. So as the rocket is falling towards Earth at 9.8 meters per second squared, it will detect that and it will turn on the LED, which will activate the parachute. Now the person who needed this circuit wanted it to be run on a Nano, so it actually did that. We got Arduino Nano, and this is the second accelerometer. This is ADXL345, and it's connected up to the Arduino Nano using the I2C bus. So I'll power this up and we'll have a look at this circuit. Okay, I got my board powered up with the ADXL345 accelerometer with my Arduino Nano. And I'm running a little program. It's written in Forth. So when the accelerometer detects a free fall, it sets off a free fall interrupt, which will be detected by the microcontroller, and it will turn on this LED indicating free fall. So I have a little setup. We'll do some drop tests and we'll see how this circuit works. Okay, I have a little setup to do some free fall tests. I put a blanket on my chair so I can take my module and I can drop it, and when she goes into free fall you can watch the LED come on. So the LED comes on and she'll go out and reset for the next test. You do it again. Now if I change the orientation of this board in any direction, the vector sum of all three axes will be 1g. So the square root of x squared plus y squared plus z squared will be 1g. And when I drop it, it'll accelerate towards my blanket at 9.8 meters per second squared, and all the axes will go to 0 G values, and we'll get a free fall condition, and the LED comes on. Okay, here's the data sheet for the Analog Devices ADXL345 accelerometer. It's a 3-axis and has programmable sensitivities from plus or minus 2G to plus or minus 16G. Now if you want to get this circuit up and running really quickly, you could just download the library for the ADXL345. But in this video, I'm going to be using direct register programming. So the rest of the video might not be for everybody. Now the heart of this accelerometer, the ADXL345, there are special function registers, and we'll have a look at them next. Okay, here's a register map for the ADXL345. So we use these registers to configure the accelerometer. Now if we look at the very left, we can see the address list. So it's from hex 0 to hex 39, and then decimal, that's 0 to 57. Now each register has a device name, a type, a reset value, and description. If we look at address 0, it's called the device ID. Now on reset, it's going to be 1110-0101, and in hex, that's E5. So this device ID is hard-coded into the accelerometer. So when we set up our I2C link and we read address 0, if we get a value of E5, we know we're communicating with the accelerometer. Now the registers that we're going to be concerned with will be the free fall threshold and the free fall time and interrupt enable. So we use the interrupt enable to enable the free fall interrupt. Then we configure our threshold and fall time, and that will give us an output when we get free fall. So now to configure these registers, the technique that I use is the same technique that I used on the registers in the Atmega 328P microcontroller. Okay, now we are looking at the data sheet of the Atmega 328P microcontroller, which is on the Nano, and these are the special function registers. And if we look at address hex 25, that's the address of port B. Now port B pin 5, which you can see here, is connected up to the LED on the Nano. That's the onboard LED. So if we set this bit 5 of port B, LED will go on. If we reset the bit, LED will go off. So we'll use the same technique that we could turn the LED on and off on the Arduino Nano. We can use that same technique to control the function registers on the accelerometer. So next we're going to have a look on how we could do that. Okay, I have TerraTerm up and running on my computer, which is connected to the Nano, which is connected to the accelerometer through the I2C bus. So next I'm going to show you a little technique where we can create a window into the microcontroller and into the accelerometer. Now remember, port B pin 5 was connected to the onboard LED, so we could have a look at port B. So port B address was 25, and we do a right arrow, and there's a value in port B. So bit 5 is 0, so my LED is off. Now if we want to turn on the LED, we go bit 5, then the address is 25, we go set. Now we have a look. Port B, you can see bit 5 is high, so my LED is on. Now we can shut off the LED. So we go bit 5, address 25, and we go reset. Now we have a look at port B again. LED is off. So we type any address at the keyboard and the right arrow will get the value of that address. So that's a little window into the microcontroller. Now we could also do that to the accelerometer. Now remember, on the accelerometer, address 0 was the device ID, which was E5. So if we go 0, that's the address, and we go a long right arrow, you see it's a long right arrow instead of a short right arrow, and there's E5. So now we're looking into the accelerometer. Now we can look at all the registers. There they all are. See, the very top is 0, and the very bottom is 39, and there's all the registers all in one swoop. Okay, so now we have a window into our microcontroller and into the accelerometer. So we could look at any RAM register address, and we could change its value right down to the bit level. Now if we look at the accelerometer registers, register hex 29 is the freefall time register. So the accelerometer has to be in freefall for a certain amount of time before we could interrupt and before the LED comes on, and we could set that in that register. Now register hex 28 is a threshold register. So when the accelerometer goes into freefall, all the G values of all axes will go to 0. But they all won't go to exactly 0 because it's not calibrated perfectly. So we could set the threshold. We could say if all axes go to 100 millig's, then that will be a free fall condition and I will get an interrupt. Now to set those conditions, to set those values, what I do, I map those registers to my keyboard. So on the keyboard I have my up arrow and my down arrow. So when I hit the up arrow, it will increment the value, and if I hit my down arrow, it will decrement the value. So it's a very fast way of doing it, so I could do some drop tests, and then I could up or down the value using my keyboard. And I have some examples of that. I've used that a lot, so I'll show some clips of other videos where I use this technique. And with the keyboard, I can move it counterclockwise to its minus 90 degree position, or I could cause it to move clockwise back to its 0 degree position and continue on to its plus 90 degree position. Okay, now I'll jump up 10 resistors at a time. And now I'll go home, I'll put the wiper to the very top, and to the bottom it'll be 0. Okay, so that's a very powerful technique where you have a window into your microcontroller through your keyboard and into the device that you are controlling. Now this could be any device. It could be a temperature sensor, a humidity sensor. It could be connected through I2C or SPI. Then you use the up-down keys to change the values of the register. And when you're using the up-down keys, you'll actually get a display of the value that you're using. And then you can use that in your main code. So it cuts down on debugging because you know it's going to work because you've tested it out in this way, direct register programming. So this is probably not for everybody, but it's what I use, and it's something you could think about.